Hi, my name is David Siegel. Today is March 25th, 2021, and today I hosted a web conversation on Zoom about climate change, and we had the pleasure of listening to Andy May for 15 minutes talk about measuring temperature.
This is just a short talk on a small part of a big problem, which is how to measure climate change. The phrase climate change is a little redundant because climate has always changed, it always will change. The whole purpose of having the term climate is to talk about how it changes. In the second order draft of AR6, which I've read, the IPCC calls temperature a key factor of the changing state of the climate, which is true. Temperature is, precipitation is, a number of other factors are as well. But we'll talk just about temperature in this one. In particular, we'll talk about global mean surface temperature, which is the measure that the IPCC has relied on to tell us how climate change is going. It's the average of land weather stations and sea surface temperatures. It's been the official IPCC measure of climate change for some time. There's been a lot written about the accuracy of the global mean surface temperature, but at least it's based on a data set, several data sets, as a matter of fact, and a lot of people who have analyzed those data sets. It was used in AR5. It was used even in the most recent 1.5 IPCC report. Now, global average temperature, it has a built-in bias because solar and orbital effects on climate are regional. They change by latitude. The southern hemisphere doesn't change in sync with the northern hemisphere or at the same rate. In fact, the southern hemisphere is warming much slower than the northern hemisphere today. Both orbital precession and orbital obliquity affect temperature by latitude. Only CO2 is perhaps global. They're masking regional changes by using a global average, and they're also emphasizing the global effect of CO2 because it disperses so rapidly. Another problem is surface weather is chaotic at all time scales. The so-called climate limit of 30 years is very arbitrary. Weather changes and climate changes at the 100-year scale and at timeframes even larger than 100 years. It also changes sometimes season by season or year by year. The July Vostok station in Antarctica has an average low temperature of minus 70 degrees C. In Doha Qatar, the average high air temperature is 41 C in the same month. So what does an average of minus 70 degrees C and plus 41 degrees C really mean? It doesn't mean very much. In the AR6 SOD, they have decided, at least so far, the final report isn't out yet and probably won't be until July, but they're replacing GMST, which with all of its problems, at least is based on data, with a new measure called GSAT, the Global Surface Air Temperature, which is from a model. It has no data set that it's based on. It has the data such as it exists, like nighttime marine air temperatures from ships, doesn't even support that GSAT is warming faster than GMST, which is what the IPCC claims. They claim that GSAT has to warm faster than GMST because their model tells them so. And that's the only thing they have that supports it. So we've got a chaotic atmosphere. We've got a new measure coming that is model-based and not data-based. And the problems I've just discussed. Okay, here's an ocean temperature profile The data is from the University of Hamburg. They have like I mentioned earlier, they have a quarter-degree latitude by quarter-degree longitude high-resolution grid that they've built with multi-year data. There's 12 data sets, one for each month. I'm showing the one for February. Most of the data shown on this plot was gathered by Argo floats or buoys between 2005 and 2015, 2004 and to 2015. Goes down to 6,500 meters. As you can see, it drops pretty fast in the upper 1,000 meters of water. The mixed layer is also shown here for February. And the mixed layer is just that tiny little bit at the top. The mixed layer is a turbulent zone. The turbulence is maintained by wind. Its thickness varies throughout the year and with wind speed, but it's got a constant temperature and a constant density almost. The general definition is usually if the temperature is within 0.5 degrees C of the surface, then that is part of the mixed layer. So 0.5 degree C isn't very much. It's basically very uniform in the mixed layer. Below the mixed layer, the age of the temperature seen in the water is dependent upon the age of the water and the temperature, and also it's dependent upon ocean current speed and direction at that depth. It would be nice to build a model rather than building an atmospheric model. It would be nice to build a model of temperature change with depth and the age of those temperatures. I think we might get a better grasp on past temperatures by looking at the deep ocean. Here's a mixed layer plot by year. The previous data was from the University of Hamburg and it's multi-year data. This is year by year data from the Japanese Agency of Marine Earth Technology. And as you can see, if you look at the global average, the ENSO events, the El Niños and the La Niñas show up really well on the mixed layer data. So the mixed layer is reflecting the surface, at least on monthly to annual type of time frames. The mixed layer has 27 times the heat capacity of the entire atmosphere. So there's a real delay in the atmosphere affecting the mixed layer. And besides the delay, the extremes that are happening in the atmosphere, the chaotic extremes, are dampened. You get a better and more stable view of what's happening on climate timescales, which is very helpful. The current trend is down. It's not very much. It's about 0.6 degrees per 100 years per century shown on here, but that's not very good, not only because the accuracy of the Argo and Triton data might be suspect, but also because in the early years from 2002 to 2005, the coverage wasn't very good. So those early years that kind of define that downward trend are not very reliable. If you were to trust this data where the coverage is pretty good, you would say that the temperature is flat. It's just not really changing significantly, except as a result of the ENSO events. Now, this is the deeper ocean. Again, it's JAMSTEC data, the Japanese data. It doesn't have any ENSO signal in it. I looked. It's basically just a linear increasing trend in temperature from 2002 to 2020 with an R squared of 0.9. I don't know how accurate this trend is. It's about 0.4 degrees per century, but The trend is increasing, and I suspect that most of this signal, this increasing trend, is natural. I doubt there's much of an anthropogenic signal in it because the water is just too deep. I don't know how the age is reflected by depth. That's why we need a model. I'm sure as you go from 100 meters to 2,000 meters, where we have most of our data, you would go through quite a lot of time. Okay, this is the last slide. The Makassar Strait lies in between Sulawesi and Borneo in Indonesia. It's one of the primary connections, especially the deep water connections, through Indonesia from the Pacific Ocean to the Indian Ocean. The water that exists in the Makassar Strait is from both those oceans, plus it's from the Southern Ocean. Some of the water is from very close to Antarctica that flows through that strait. What Rosenthal did was he looked at a particular foraminifera that lives at about 500 meters. And he built a paleo temperature record that we're looking at here using those forams. And he claims an accuracy of plus or minus 0.3 degrees C, which I'm sure Pat will object to. But that's what he determined in his paper in Science in 2013. So the record is just of the Makassar Strait, but it is really a record of water at 500 meters all the way from the northern Pacific to Antarctica. You can clearly see on his record that the Holocene climatic optimum from about 7,000 BC to 4,000 BC is very high. It's around 10 degrees C in that strait. And then we start the neoglacial decline, which goes to the medieval warm period about 1,000 years ago. And the medieval warm period in that strait at 500 meters is around 8.5 degrees. Then the temperature falls rapidly down to a minimum in the Little Ice Age. And in the Makassar Strait, the minimum is reached in 1810 AD, and it's 7.2 degrees in that year. And then it begins to climb as we come out of the Little Ice Age in the 19th century. The last point in his paleo temperature record is about 1930. So today, we can go to the University of Hamburg temperature profile, the detailed profile, the multi-year profile, and look at the Makassar Strait. And we can see that at 500 meters over the period covered, 2004 to 2016, the temperature is 7.7 degrees C, which is about a half a degree warmer than it was in 1810. It's not kosher to combine instrumental data with proxy data, but if we were to do that, we would see a half a degree increase in that strait at 500 meters today from the lows of the Little Ice Age. The main point I'm making here is that the data we need to reconstruct the Holocene in older temperatures is probably in the oceans and in the ocean sediments. I don't think we're going to find anything in atmospheric proxies or atmospheric data that's going to help us, because weather changes too much at every areal scale and at every temperature scale. It's just, atmospheric weather is just too chaotic to build a record with. Ocean temperature reconstructions represent much more of the Earth's surface, because the oceans cover 71% of the surface. Land only covers about 29%. So an ice-covered land, which is where we get a lot of our better data, is even less than that, and just around the poles. So that's the end of my presentation. I'll turn off my share, and I'll entertain questions.
Andy, Can you go through your calculation of the 99% of the heat coming from the sun, or the change in flux maybe goes into the oceans and not into the land?
Right. The high heat capacity of the ocean stores much more thermal energy or heat than the atmosphere does. So if we ignore land, which is too complicated to figure out, the heat capacity of land changes with multiple factors. So we just ignore the land surface. Just consider the ocean and the atmosphere. 99.9% of the thermal energy is in the oceans, and less than 0.1% is in the atmosphere.
Andy, great virtually meeting you. I really respect a lot of what you had to say and have said over the years. My question is, solar cycles 24 through 27, is a new solar grand minimum coming? Any thoughts on that?
I really don't know. I'm the wrong person to ask. Certainly, we had a pretty powerful La Nina this year. It's quite possible we'll have another one next year. So I would think that, you know, the next couple of years are going to be cool. The long-term trend, according to Javier Vinos, who I very highly respect, he's done a good job of sorting a lot of this solar stuff out. He tends to think that the overall trend is going to be warming for the next few hundred years. And then we'll go into a cooling trend and probably into the next glacial advance, which is what we really need to be concerned about. But short-term wise, probably it's going to be cooler for the next year at least. But I don't know beyond that really.
Andy, you're saying that Javier's work is really orbital. It's not about sunspots.
Right. He's of the opinion, and I agree with him, that the major impacts on our climate are orbital variations. And the neoglacial period, which we looked at in the last slide, is definitely orbital obliquity caused. Once we get to the next glacial advance, that will also be obliquity plus precession that leads us into that. That's probably over 1,000 years in the future, but the solar variability in and of itself is poorly understood. Nicola Scafetta has done a lot of work on that. I think that probably there is more variability than the IPCC is assuming. They're assuming it's really just a solar cycle. They don't think there's anything more to it. But there's no other star like our sun that's like that. They're all more variable than that. And when you get out 100, 200 years or more, I think there's more solar variability, and that may play a role. Now, how it does it, I don't know. Could it be the solar wind, which are particles from the sun, or is it the changes in the solar magnetic field, or is it something else? I don't know. But there's got to be more variability than the IPCC is assuming, I think.
Dick Linson pointed out that there can be variations, relatively small ones, but significant, in the climate without any changes at all in the amount of energy that's falling on Earth.
Right.
And probably the way that arises is that the climate consists of a bunch of coupled oscillators, the various ocean basins, for example, in the atmosphere, and they swap energy around the way coupled oscillators do. So you can have air temperature rising and falling because it's coupled to some other oscillator that's transferring energy into it without any change at all in insulation. And
Right.
so a lot of these variations that we see that are relatively chaotic probably come from processes like that. And they're completely unpredictable.
I agree. And internal variability, the IPCC famously assumes is zero over 50 years. And That's very unlikely because there probably is internal variability at the 1,000-year scale, for sure.
If I could just say also that Jim Hansen supposed that internal variability was the plus or minus 0.13 of a degree that he saw in his normal period from 1951 to 1980. And that's where he got his 99% certainty that, you know, climate change was upon us because the temperature had increased more than 0.39 of a degree. And it's complete and utter nonsense. But that's the kind of thinking that typifies the whole field.
Yeah, I'm shocked that there's singular focus on the atmosphere. I mean, we live in the atmosphere. I mean, there's some justification for it, but they are not considering the oceans, which is most of the Earth.
Yeah. Carl Wunsch points out that the ocean model parts of AOGCMs don't converge. And when he points that out to climate modelers and to ocean physical oceanographers, they shrug and say, well, it looks reasonable. So, you know, what kind of predictions can you make with a model that doesn't converge?
Right.
It's another thing they completely ignore.
Yeah, I used to write climate model. I mean, I used to write petrophysical models for a living, and as a former computer modeler, I'm horrified.
Yeah.
I'm horrified by the whole concept of averaging different models, for one thing.
Yeah. Chris Essex pointed out in a paper years ago that a global temperature doesn't exist. And that's been ignored too. He did, you know, went through the calculation and published on that. And
He's quite right.
yeah, and it plays exactly into what you were talking about, you know.
Yeah. Any other comments or questions?
Well, Svensmark has a real interesting take on cosmic ray, cloud forming, cooling, and solar wind and more active sun, keeping fewer cosmic ray impacts into the atmosphere versus weaker sun, allowing more cosmic ray, cloud forming, cooling. So that's an interesting area.
Shadiv and Svensmark have both done some brilliant work in that area. I wish we could be more definite about that because it's a fascinating idea.
What about Near's idea of moving through the arms of the galaxy?
I think that makes some sense. I'm not willing to discount that idea.
I don't understand how one star moves through the arms. Isn't it part of one arm? That's what an arm is. It's a bunch of.
It's a local phenomenon, a galactic point of view. The arms will probably change shape over very long times, and the sun is just traversing the local arm. Is all.
Huh. I still don't get that. I'll have to understand.
You need to become more godlike, David. That's all.
Well, working at Slack will do that, Pat.
Yeah.